Okay, everybody, welcome to another session of the 10th seminar series. Today we have Rebekah. She will be speaking to you guys about life cycle assessment, specifically on asphalt pavements. Rebekah actually did her bachelor's just outside of Philadelphia before coming to UC, where she completed her master's about a year ago, correct?
Summer.
The summer? Not quite a year. And currently working on the PhD under the guidance of Professor Asphalt. So please join me in welcoming Rebekah.
Hey, thank you very much. I'm Rebekah, as Aaron just mentioned, and my talk is titled Life Cycle Assessment for Asphalt Pavements with Regional Asphalt Binder Production Models. Okay. So the outline for this talk, I'll start with an introduction and background, and then talk a bit about life cycle assessment, or LCA for pavements. The bulk of the talk will be on the regional asphalt binder production models, the development of these models. I'll give a case study and then end with the summary. So the work presented in the presentation today is actually part of a larger body of work, a larger project that is for the Illinois Tollway Authority. And the main objective of this project is to develop a complete roadside life cycle assessment toolkit. So the toolkit consists of 5 different modules: the pavements module, drainage, structures, lighting, and landscape. And the university here is working with 5 research associates and the right environment to come up with these modules. And today I'll be mostly focusing on the Pavement LCA module, so that's highlighted. So the particular objectives of the work that I'm going to talk about today is to develop a regional inventory model for asphalt binder production that can be used in Pavement LCA. So there are a couple of different sub-objectives or motivations for this. The first is to be able to capture major regional differences in the production of asphalt binder in different regions of the U.S. The second is to be able to use updatable and open source data to be able to come up with the information for these models. And the third is so that we can develop a streamlined approach that easily consider different parameters in producing binder and be able to apply it to different regions very quickly and even different petroleum products. I'll talk about later. So a quick background on LCA. LCA is a method to assess the cradle-to-grave interactions between the environment and a product system. So generally we have 4 different stages of the product life cycle: the materials, assembly, construction, use of the product, and finally disposal or recycling. So what LCA, we look at when we perform LCA is all of the inputs, environmental inputs, the energy and raw materials that go into the different processes in each of these stages, and then the environmental outputs, or the emissions to air, water, and soil, and so on. So there are a couple of different motivations as to why we would use LCA. The first one is so that we can accurately quantify environmental impacts. There are some ways to do qualitative analysis of environmental impacts and systems, but we can actually get numbers in this case about energy usage and global warming potential and so on. We can also use LCA to evaluate improvements in sustainability goals from past to present, for example. We can determine where investment can be most effective. We can figure out which stage in the life cycle we can improve on. So LCA is part of a larger holistic sustainability program. The first is the life cycle assessment, which is the environmental component. The second component is economic component, which is life cycle cost analysis. And the third is social component, which is usually evaluated with a sustainable rating system, such as the LEED system with buildings. So for pavement specifically, it's a fairly new application of LCA over the last decade or so. Things have really been established. So currently there's some work to establish an LCA framework for pavements. And this diagram here is adopted from a workshop about 2 years ago. And generally now we agree upon about 5 different phases in the pavement life cycle. Materials, extraction of materials and production. We have construction, which includes all the equipment associated with constructing the road, as well as traffic delay, transportation, and so on. We have the use phase, which is currently has the most research gap, research needs right now, and this can include things like carbonation of the concrete pavements, lighting, albedo, rolling resistance. And then we have maintenance, which feeds back into materials and construction. And finally, end of life, which includes landfilling or recycling and transportation and so on. And just like with other LCA systems, we're also looking at the environmental, energy and materials, as well as the environmental outputs, emissions to air, water, and soil. So to give you an idea of the contribution from each of these 5 phases, of course this can vary depending on the project itself and on what environmental impacts you're looking at. But a typical example of asphalt pavement life cycle for energy, you can see the contribution from the materials production phase is about 4 or 5%. The construction phase is about 1 or 2%. The maintenance, again, about 3 or 4%. The use phase, which 80 to 89%, as you can see here. And finally, end of life, which is usually a very small percentage, depending on the scenario that you're using. So there are different steps that have been given by the International Standards Organization to perform LCA, and these are guidelines that are pretty vague and can be used for any product system. So the first is to define the goal of the LCA study. The second is the inventory analysis, which will be a big part of what I'll be talking about today. And then we have impact assessment, and finally interpretation. So the inventory analysis contains life cycle inventory data, the LCI data, and this is a collection of the data, the validation, the analysis of all the data. And in general, the data should be regionally sensitive and also time sensitive to better represent the product system that you're evaluating. And these are two important concepts that will be coming up later in our models. The inventory database, so some processes that we'll be considering, material production and processing, processes for fuel production and energy generation, electricity generation, equipment usage for construction, hauling and transport. These are the main processes that are usually considered in a pavement LCA. And the process that we'll be focusing on today, the asphalt binder production, fits into the very first category. Different sources that you can use to collect LCA data include getting the data from existing public or commercial LCA databases, published literature, government support reports, our industry reports, and also local surveys. Those are available. So the motivation for pursuing the development of asphalt binder LCA model is due to the environmental contribution of this product to the raw materials in the production phase. So as you can see, a typical hot mix asphalt mix has maybe 5 or 6% of asphalt by weight in the mix design. However, it can contribute up to 90% of the energy in global warming potential, or greenhouse gases for the materials that are used in the mix. So as you can probably gather, an LCA is a very very data intensive process. So to be able to focus on the key elements, the key processes that will contribute the most to the LCA is very important when you're limited in time and resources. So some existing information that is already out there for asphalt binder. There are a couple LCI lifecycle inventory studies that have been performed. A lot of these are performed in general for petroleum products, specifically transportation fuels like diesel, gasoline, jet fuel, because these are really big contributors in our transportation system for vehicles. So there have been studies conducted to figure out global warming potential that is required to produce gasoline, diesel, jet fuel. For asphalt binder, there have actually been some specific studies that have been done to collect LCI data. Some of these studies you can see are from other countries like Sweden, North America, Europe, and tend to be a little bit outdated in the last 15 years or so. And there are no regional U.S. models. And we'll find out later why it's important that we consider regional aspects in asphalt binder LCA. So other LCI data sources that we'll be using in the models are public sources and commercial sources. So the public sources are from the U.S. Energy Information Administration. They publish a lot of information about petroleum movements, where petroleum comes from, that go into the refineries in the U.S., and also what types of fuels and what percentages of the fuels are being combusted in the refineries. They have a lot of open source data about that that's published pretty regularly. We also are looking at commercial databases such as US EcoInvent 2.2, and these contain unit processes that can be used to model the environmental impacts that we need in SEMA-Pro and other commercial LCA software. Okay, so the modeling approach that we're taking is we're collecting higher level data from these open source public sources that I was talking about in the previous slide, and we'll use these higher level sources to choose the appropriate unit processes from commercial LCA databases, and then model all the processes and finally the product system in SEMA-Pro, which is a commercial LCA software that's used for modeling. The system boundaries of this model include, so it includes what's not in the dotted lines here. So that is domestic and foreign crude oil extraction and flaring, transportation, and then domestic refined transportation and storage. So we're not including any foreign refining or foreign refined transportation from the U.S. The cutoff is here. Any foreign processes. And we'll be including all of the upstream processes needed in each of these major processes here, such as the generation of the fuels that go into extraction, like generation of electricity, and so on. So there'll be three major production stages involved in the modeling of asphalt binder. The first is crude oil extraction and flaring, and this is for foreign and domestic sources. The second is petroleum refinery, and this is just domestic in the U.S. And the third is asphalt storage, which is again domestic in the U.S. And then all the transportation that is required between these stages. So in the 1940s, the U.S. divided up the country into 5 different petroleum administration for defense districts, or PADs, and they're still being used right now. And this is how the U.S. Information Administration categorizes their data. So you can see here the first PAD is the East Coast, the second is the Midwest, where we're located. The third is the Gulf Coast, the fourth is the Rocky Mountains, and the fifth is the West Coast. So these are the different regions that we'll be modeling. So the first stage is crude oil extraction and flaring. So as you can imagine, the crude oil that goes into the refineries in regions actually comes from very different sources. So I'm going to just give 2 examples, but they're actually fairly different for all 5 different regions. So for the Midwest where we are, we can see that about 57% of the crude oil in those refineries in the Midwest come from the U.S. The remainder, 43% come from foreign sources. And majority of those are from Canada, about 38%, whereas the rest are from overseas. And you can see how that might affect the transportation of these crude oil sources pretty significantly. In the Gulf Coast, we have a different scenario. About 25% of crude oil in refineries in the Gulf Coast are from the U.S. And then large percentage of the remainder from Mexico and South America, and then we also have some coming from the Mid East and Africa, as you can see. So this will definitely contribute a lot to the different emissions and impacts depending on where the crude is coming from. And also to give you an idea of how extraction processes can also have different environmental impacts depending on the region. We have some data here from North America, Africa, the Mid East, and then Nigeria. You can see how the energy and global warming potential of the greenhouse gases are pretty different for each region. And a large contribution to this is due to flaring. So when we extract crude oil, there is a significant amount of natural gas that comes up with the oil. And for some countries, they might not have the infrastructure to be able to capture gas and transport it and use it, so they end up flaring it or venting it. So for example, Nigeria, you can see here, has quite a lot of flaring. So that definitely contributes significantly to the environmental impacts from extracting oil in that country.
So the next
stage is refining,
and
there are different types of fuels that are used in refineries. These have been collected and organized by region by the Energy Information Administration. And they put this on publicly online, so it's very accessible.
so you can see
here a lot of it is still gas or refinery gas. And then we also use a lot of natural gas in the U.S. Pet coke, and then we purchase steam and electricity, other fuels to do the refining at these facilities.
So
each of these fuels also are combusted differently. So for example, diesel can be combusted in a stationary engine, in an industrial boiler, and so on. And this would contribute differently to the emissions that come out from combusting these fuels.
So
the Greek model that's been developed by Oregon National Laboratory actually has different breakdowns of the types of combustion these fuels undergo at refineries. So we've used those to help us model how these fuels are combusted. And one other thing to point out is electricity, which is about 5% of the U.S. average fuel that's our energy that's used at refineries. Can also vary differently depending on the electricity grid mix in the region. So this is something that we've also considered. So you can see the different regions have different amounts of energy that are used to generate electricity. And they also use different sources of non-renewable and renewable energy, which can contribute a lot to the emissions due to generating a kilowatt of electricity in these regions.
So also with
refining, we can look at the residue rates that occurs.
So
this is by mass. If 1 ton of crude oil goes through the refinery,
or 1
ton of petroleum product is produced out of the refinery. What percentage by mass is Asphalt? And you can see in different regions that this percentage varies. Usually around 7%, but it can be as low as almost 2%.
And then
we also look at plant efficiencies. So refineries, we can calculate their efficiencies by taking the total energy output divided by the total energy input. And you can see it's about 90%, 86%. But it does vary for each region. So these are all things that we consider when we're looking at refinery processes in the 5 different regions.
And then finally,
a big variable in refining is how we allocate the energy and emissions to different products that come out of it. So allocation is the concept that's defined in the International Standards Organization as partitioning the input or output flows of a process or product system between the product system and one or more other product systems not in the study. So for example, refinery has multi outputs.
So it takes crude oil,
but it spits out a lot of different petroleum products, and one of these is asphalt. So we need to figure out how to allocate the correct amount of energy emissions, energy and environmental impacts are attributed to asphalt. So studies do this in a number of different ways. Some people use physical parameters like mass, volume, or energy content, and other studies will use non-physical parameters like market value and economic value. So in our study, we've used economic value, but we'll see through a sensitivity analysis how it differs if we use different types of allocation.
So with the
U.S. economic allocation,
you can see here
how asphalt relates to other products such as gasoline and diesel, which typically have higher market value
than
asphalt.
In the final stage,
in asphalt binder production is storage of the asphalt.
So this
using a combination of literature and those local surveys, we've seen that the asphalt is stored for 30 days, for 24 hours per day at 300 degrees Fahrenheit, and natural gas is used as the fuel source.
So in summary,
There are again different, a lot of different impacts that we can use. But here we look at greenhouse gases, and we can look at the contribution for each of the stages, each of the processes. So first we have extraction, which is about 40% of the greenhouse gases. Flaring, which is about 6%. Domestic transportation within the U.S., about 4%. Foreign transportation from overseas, 5%. Refining, about 44%. Refined transportation to storage location, 2%. Refinery storage, about 1%. So again, these percentages, as you can see, will actually vary depending on the region. So this is for the average U.S. production of asphalt binder. So if we look at the other regions, so we just talked about the U.S. average here, you can see that there is quite a big difference. And again, depends a lot on where the crude sources are coming from, and also the refineries. Those are usually the two major sources of variation. We can also see on the right side different literature values that have been reported, and some of these literature values are used pretty widely in pavement LCA studies at this point. And you can see that there is quite a variation between them. You can imagine what will happen if you use one value versus another and how that will affect the results. So one other topic that we should cover is feedstock energy, which is usually defined as the energy that is embodied in a product. This is a lot more straightforward for petroleum items like gasoline and diesel, which are burned for energy, and that's definitely it's very clear that they have feedstock energy. But for asphalt binder, this is still kind of a contested area because we don't usually use asphalt for fuel. But if we do consider feedstock energy and the energy that's embodied in asphalt, you can see that it's about 7 times greater than the process energy. So typically what people do with LCA studies is report this value separately because we don't really know. There's not really a consensus right now in how to deal with this. So an example of the effect of using regional models, binder models, on just a small product system producing an HMA mix with 5% binder. So we can see here the baseline is 0, and that is U.S. average mix, and then the various lines here within the different regions that are being used. So usually we just look at global warming potential, and you can see there's about a 20% variation. And then total energy, which is probably around 10% total variation, depending on which region we use. But if we look at some other different impacts, for example, ozone depletion, that's quite a big percentage. I think it's maybe 250% range, as well as some of these other areas. So it's definitely interesting. Definitely something you can keep in mind, that just at global warming and energy, but there are many other impacts that also should be considered. So in expanding the model, there are about 15 different petroleum products that the Energy Information Administration keeps information on in their database. So we've looked at just the asphalt, road oil category, but there are 15. As you can imagine, we can take the model that we have and expand it to all of these 15 products. A lot of the processes, the crude oil extraction and so on, are similar. We can also look at many different impacts here. So 10 of these impacts are from the Environmental Protection Agency's Tracy impact method, and we also have total energy here as well. So we've developed a streamlined method where there's an equation that you can plug in parameters to and be able to find the impacts for any of those 11 environmental impacts for any of the 15 petroleum products. And basically this follows the same procedure as we just went through with the model. So we have extraction, and then transportation by overseas tanker, transportation by land, and pipeline, refining, which considers allocation and efficiency, transportation of the refined product to storage areas, and this can be done using pipelines or rail cars or many different things. And then finally storage. So if we just do a quick comparison, this is the 15 different petroleum products out there, and there are 2 different allocations that are used. One is economic in blue, and one is energy content in red. and it's showing the greenhouse gases for different products.
You can see that
There is a bit of a variation, especially in lubricants. The economic value for lubricants is extremely high by mass relative to other products. So this can give us a very streamlined, very quick glimpse of the results for different environmental impacts.
Okay, so now
moving on to the case study. So we're looking at now the full pavement life cycle. So this includes all 5 stages. And the case study is based on a reconstruction project done in 2008 by the tolling. It's 5 miles. It's a full depth asphalt pavement. Includes all the layers above the subgrade. Has outer and inner shoulders. We're looking at a 60-year analysis period. The traffic is about 66,080. The growth is 2%, almost 2%, and the trucks is about 11% trucks.
So we
used actual mixes and the predicted maintenance schedule that the tollway uses. And for the use phase, we did a more simplified analysis at this point because there's more work being done on it currently, where we extrapolated an IRA progression from historical data for these particular segments to figure out the extra fuel consumption due to rolling resistance. So the Pavement LCA tool that we used is a spreadsheet tool that has been developed by the university for the Illinois Tollway, and it includes inventory data for many of the products, many of the processes that we need, not just for asphalt binder production. So going through the life cycle phases, the first is the material production, and again, all layers above the subgrade were considered. We have construction, which includes transportation of the materials to the site, as well as constructing the road itself. Maintenance, a 60-year maintenance schedule was used. So it includes regular intervals of routing and sealing cracks, overlays, patching, record surfacing. The use, we considered just IRA and extra fuel consumption from that roughness. And finally, end of life, we considered just milling and transporting the pavement, and we assumed that it would be used as recycled asphalt pavement. No landfilling was done. So just to talk briefly about the use phase. You can see here this is the extracted predicted IRI progression throughout the 60 years, and we also have the extra fuel consumption that correlates directly to the IRI. So the extra fuel consumption due to IRA over 60 years is about 161 million kilograms of CO2. And if we compare that to the albedo effect of radiative forcing, this occurs when a new surface is made like an overlay. It's a one-time event. So if we consider just one of these new overlays, it's about 2.3 million kilograms of CO2. So that's about 1.4% of the greenhouse gases compared to the IRI related greenhouse gases. So it's definitely shows that the IRI is overshadowing the albedo effects for radiative forcing. So that's just to give you an idea of the use phase elements. And then if you look at the entire life cycle and the results, we can see definitely that the majority of energy, which is in blue, and the global warming potential or greenhouse gases, which is in red, is the use phase. It's about 91 to 92% for these two impacts. And as you can see, the remainder of the phases contribute maybe 4% at most. So if you look at the effects of using a regional binder model, so for the case study we used the Midwest region asphalt binder model because we were looking at the state of Illinois. So if you look at different regions, so again the 0% is using the U.S. average, and here we have one East Coast, Midwest, Gulf Coast, Rocky Mountains, and West Coast. We can see that with the use phase, considering the entire life cycle, the use phase overshadows pretty much all of the effects of energy and greenhouse gases. So the difference of using different regional models is less than 1%. But if we take out the use phase and look just at the material, just look at the phases, the other phases, we can see that the differences go up to a range of 6 to 8%. energy, and then a little bit more for greenhouse gases. What's interesting is if we look at other impacts. So, for example, ozone depletion, just saw earlier, had a very big variation due to regions. We can see that the difference is a bit higher at 20% range. And then if you look at non-carcinogenics, it's quite a bit higher and reaches a range of about 70% difference. So this shows that there could be a good reason to look at other impacts besides energy and greenhouse gases. So if we look at some other impacts, so this is greenhouse gases, global warming potential, and we can definitely see the use phase, which is phase number 4, has the highest impact. But if we look at something like respiratory effects, which particulate matters will contribute quite a lot to that, then the materials and construction phases are starting to show a little bit more as compared to the use phase. And then we have ecotoxicity, which the phases are a lot more equal, and finally carcinogenics, where actually the materials phases and maintenance phases are quite a bit higher. A lot of people tend to look at greenhouse gases and energy because they're a lot more straightforward impacts. And things like respiratory effects, ecotoxicity, carcinogenics are a lot more complicated as to what influences them. So definitely a lot more research is needed before any concrete results or observations can be made about this. So some future work. So specifically for the asphalt Pavement model, something that we did not address is the effect of oil sands. And research or literature has shown that oil sands does have a significant effect on environmental impacts. It takes a lot more energy to extract oil from oil sands, and sometimes you have to upgrade it before you refine it. So this is something that we should continue to work on incorporating. And then in general with the Pavement LCA, the university research group here has been working on improving the use phase to expand it to include deflection and texture-related roughness effects. We're also working on improving the end-of-life scenarios to include other options. And we're also working on creating a tool right now that is based on pay items rather than design aspects to make it easier to incorporate for different agencies. So this work is funded by the Illinois Tollway through the Illinois Center for Transportation. And there are a lot of people that have been involved in this project, specifically Steve Gillen from the Tollway, Applied Research Associates, the Right Environment, and many people from the U of I, including professors Imad Kai and Hassan Ozer, Sangu Khan, and many other students that would take a while to name. So, thank you very much. Thank you very much. Yes. Yes. For oil extraction. Okay. So the system boundaries. So that includes like on-site extraction of the oil and then transporting it to the refinery. Was there another specific and flaring of the entire analysis? Should I? See if I can. Okay. So were you talking about this slide, the system boundaries, or? Yeah. Yes. Okay. So the crude extraction itself, we used a process from SEMA Pro. Their system boundaries includes any of the equipment, energy needed to extract the oil to bring it up from the bottom, like to the surface, and also venting of any natural gas and flaring of any natural gas, and then it's kind of related to transporting it to a port and then to the U.S. So is that answering the question?
Yeah. Also, another question.
Yes. Yes.
What's the difference between source or
This one? This one, okay.
Right. So,
It is showing the breakdown of the stages. So you can see, for example, the East Coast, the extraction has a really high contribution compared to the other ones. I would guess, I don't have the numbers right now, but they probably have a lot of oil, for example, from Nigeria, because that has a lot of, the extraction, the environmental burden from extracting from Nigeria is very heavy compared to the other countries. And then you can see also there's a lot of transportation, so it probably gets a lot of crude oil from overseas, whereas for example, the Rockies probably get almost all of their oil from, I think, Canada, which is very close. They're not really transporting much. They're not transporting across the world or anything, or across the Pacific. And then the refinery does have a little, not as much, but it's probably mostly the extraction and transporting of the oil. Yeah. We tried to make them as similar as possible, so you can see not all of these studies are very transparent. Also, so we did make sure to include all of the production of fuels and electricity. But I think a lot of these studies don't consider storage, for example. But that was a pretty small percentage, so it probably won't make too much of a difference. But they should include the major extraction, refining, and transportation processes, which are the biggest contributors.
On slide 7,
Oh yes. Sorry, that should be per ton. Yeah.
So what's your estimation if you consider including
Oil sands? I think there's some literature values that say it could increase by. It depends on what percentage it is of the profile of the crude that you're using in the refinery. But I would expect maybe up to 20% of the difference. So it is quite a lot. Yeah, the final. It could be. But it also depends on regions, because some, like the Rockies, rely a lot on Canadian oils, which is usually 50% of it is oil sands. So that would probably have a bigger difference there. But yes.
You also do a preliminary study how it affects different regions, the percentage changes, how it changes, how it affects.
Right. And that would be very pretty facilitated to do with the streamlined model that we have, because if you just change the distribution of the sources and the percentages, the shares, then you would be able to do a parametric study pretty easily. Because I think oil is governed by a lot of geopolitics, so that can definitely change things in the next 10 years. The distribution could be completely different.
What would you suggest say distribution of oil from
Yeah, I think that would be pretty difficult. It's hard to predict what will happen in 10 years, because the politics are changing so much, especially in regions that are extracting oil. So we could look at historical data and kind of look for patterns in that and try to incorporate some sort of uncertainty and maybe do multicolor or something. But I think it would be pretty difficult to accurately capture uncertainty.
When you discuss on those before attacks.
That's a good question. I'm not sure, but I would assume it's before. It was published for each state for each year, so it was averaged. But that's a good point. But
Regulations that could impact your choice of allocation. You found that the economic allocation was best in this case, but there are so many factors that might really be seen as a disadvantage of economic allocation, given that which very well in this case.
Right. It's true.
And one question I forgot. You used in your simulations the case study.
The case study.
Did you use the regional model for these fuels too?
I did not. I did not.
You used to use it. Basically, you one energy consumption with vehicles operations and those vehicles use regional fuels that also in your results, right?
Right. So with our streamlined model, we could actually use those fuels from the models into different aspects, different parts of the LCA the life cycle.
Any other questions? Thank you.
Thank you.